Hello, everyone. My name is Kyusang Lee from the University of Virginia. Today, I'm going to talk about the defect identification technology using the edge computing hardware. Especially here, we have employed hardware and software co-design method to enable the power-efficient feature extraction that could be applied in various fields, including the semiconductor industry, biology, and medical applications. Here's the motivation of this work. Automated defect identification is a significant task in many fields. As you could see from below figures, in the science field, identification of defects in the material is one of the indications to measure the material quality, as well as to predict the device performance. Also, in the industry, defect identification is one of the major challenges to reduce the failure of system and to improve the production yield. Also, in medical application, finding the defects in the medical image is critical task for the healthcare. To efficiently perform the defect identification, it is also important to develop the power efficient algorithm that is also comparable to the current technology. And to enable the power efficient and CMOS process comparable hardware for defect detection, we have combined the two technology. One is the MEMSter and the other is the oxide thin film transistor via the heterogeneous integrated hardware and software co-design system by embedded morphological image processing algorithm. First, MapMister is a simple two-terminal non-volatile memory that could be used for the analog computing at low power consumption. And oxide transistor is widely used technology for the flexible and transparent electronic, which is also CMOS process comparable. So this is very advantageous for the heterogeneous integrated system. And by combining those two hardware, and then we are kind of embedded the morphological image processing algorithm. So we were kind of able to demonstrate the efficient defect detection process. Here, the figure shows the schematic illustration and optical microscope and SEM images for one transistor and one MEMSer crossbar array. Here we have employed one transistor, one MEMSer structure to reduce the sneak path and to enable the precise conductance control at low power consumption. Basically, transistor is used to control the weight value of the MEMSer by applying the voltage to the gate so that it control the field to the MEMSer comprised of the hafnium oxide. And cross-sectional schematics, those below schematic shows the cross-section view of the our 1T1R system, that is the integrated transistor and a MEMSer on top of it. And using the those one transistor, one MEMSer crossbar array, so we demonstrate the defect identification process embedded morphological image processing. Here we employ the dynamic Gaussian blur kernels with multiple sigma values by controlling the weight value of the 1T1R array to process the convolution neural network at low power compared to the digital implementation. Therefore, we were able to achieve the enhanced defect detection performance using the dedicated hardware system for those 9 different blur kernels to operate those algorithms. Demonstrate the morphological image process based on the neuromorphic hardware. First, we characterize the single oxide transistor and single hafnium oxide MEMSer separately. As you could see from the below figures, So indium zinc oxide based transistor shows the reasonably high carrier mobility, which is the instead of the left below figures. Also, it shows the low of current, which is general property of the oxide transistor. Also, the hafnium oxide based MEMSR, which is fabricated using the ALD process, shows the reasonably high on-off ratio that is sufficient to process the analog proposed. Then we have characterized the heterogeneous integrated one transistor, one MEMSR system to confirm the functionality to implement those image processing algorithm. And we were able to operate this 1T1R array under the various conditions to confirm the capability for the analog computing. And we tested this system over 200 cycles, and it shows about 6-bit bandwidth for the analog computing operation. And as you can see from those top figures, it shows the reliable performance for the off current and then on state. Also, it shows the reasonably high bit that is sufficient to operate our algorithm for the image processing. Then, using the fabricated one transistor and one MEMSR array, we apply the Gaussian kernels operation. As you can see from the below figures, we have set the targeted 9 kernels with different signal values from 0.7 to 1.1 to achieve the 9 different images from the single input images. And we were able to set those weight values using the one transistor, one MEMSR array to operate the algorithm by applying the different gate volt to the system. So we were able to demonstrate the target value using the hardware as we kind of simulated, as you can see from the below figures. And using those 9 Gaussian kernels, we have processed the defect defect detection using the as shown fabric patterns and through the distinction, binarization, and linear operation process. Then we were able to achieve 9 different images that could be combined into the one process output. So we have used those 9 Gaussian blurred kernel that's shown in previous slide, which is set by the 1T1R system through the those hardware. And through those Gaussian blurred kernel, we were able to achieve 9 different images from the single input, and we combine those 9 output images into the single one process output. And as you can see from the right below figure, it is clearly seen the we were able to extract the defect from those uniform fabric patterns. And we have applied the identical hardware and software co-design system to detect the brain tumors and skin cancer, defect in the CBD grown graphene film, and then copper film. And as you could clearly see from the images, we were able to efficiently identify various defects using our system, which confirmed the feasibility of our system for many different various fields, which is applicable using the single algorithm and then single hardware, which is universal. To summarize my talk, so we have combined hardware system and software algorithm to process the data here, which is the defect identification process. But we believe this system could be not only for the defect identification, but also could be used for the various application toward the artificial intelligence on things. So we probed here we just probed one of the potential for their use in many different fields. And thank you very much for your attention. And if you have questions, please feel free to contact me through those emails. And